Hello guys, welcome back to the channel, and in our fifth part of our road to quantum field theory, we are going to finally start tackling the big notion of quantum mechanics, or at least the non-relativistic case of quantum mechanics. This fifth part of our road to quantum field theory will not be as heavy on the math as the previous four parts, but it will, however, contain a little bit of a history and motivation as to why we are interested in using quantum mechanics to begin with to describe things such as fundamental particle interactions to even other applications of theories like quantum field theory. So to start off, mainly we are going to be looking at some of the classical failures, basically, of classical mechanics. That sounds like a mouthful, but we will start by describing some of the things which were discovered in the 19th century to the early 20th century, which were failed to be explained by classical theories of physics, such as classical mechanics, thermodynamics, and such, and how quantum mechanics gave light to those things. And afterwards, we will look at how some people kind of formalized and crammed together some of the results which we found from trying to explain these experimental gaps in our knowledge to make it into the more formal thing we know today as quantum mechanics. So we're going to go from discoveries of people like Bohr, Planck, Einstein, Dirac, and kind of summing over everything and making it into a nice coherent picture. So without distracting you further, let's actually jump into it. So if you've heard about quantum mechanics, you heard that in essence is the physics used to describe really small microscopic things. And in a lot of sense, that is indeed the case. You can extend the notion of quantum mechanics a little bit further, especially when dealing with solids and the behavior of how things in solids work, which is on the macro scale. But still, regardless, for all general sense and purposes, as well as for historical notes, indeed, quantum mechanics was used to describe a lot of things which were happening on the really tiny scales, on the microscopic scale. So one of the experimental things which were failed to be explained by classical physics to begin with, the most famous one very likely that you know of, is the black body problem. And that is that if you have radiation being emitted from some sort of radiating source, like let's say you have a piece of metal, I don't know, something like this, like an iron rod or something, and it's radiating away heat. Well, according to classical thermodynamics, the way the relation basically between the temperature being emitted as well as the wavelength of the thing being emitted. So if I put wavelength and temperature right here, that would look something along these lines. Well, that is at least if you're going more and more towards the ultraviolet range of the wavelength, so towards smaller and smaller wavelengths. At longer and longer wavelengths, you have the curve looking a little bit more like this, which implies basically that the longer the wavelengths of lights being emitted from, let's say, our piece of a metal bar, then the lower the temperature. So if you saw metal being like heated, it starts out with this light reddish color, and then it becomes a little bit more orangey, and then it like eventually starts radiating more and more light to some or higher colors of light, you could say, up to the point at which it starts glowing white. As a matter of fact, this is the same notion which allows astronomers to know what stars or the temperature of stars. By looking at whether a star is blue or red, you kind of have an indication as to how hot the surface, at least, of that star is. So at around 100 something nanometers, I'm really bad with a specific number, but perhaps I will put it down there. At the ultraviolet wavelengths, you start getting that this curve kind of blows up to infinity. And in physics, usually when things blow up to infinity, that tends to either allude very likely to a problem, especially when the thing that is blowing up to infinity is something that is supposed to be a finite value. And in this case, what would infinite temperature be? Like it wouldn't make a lot of sense to have a quantity such as temperature blowing up to infinity. If this was just the orbit of something, and if you're saying that if you have a planet and if you give it a little bit of a push, at some point, if it's so far away from the thing it's being attracted to, that if you give it a push, then the force that is being impacted on it goes to infinity. That makes a little bit more sense because that implies basically that if you give that planet a little bit of a push, and if it's sufficiently far away from the thing that is attracting it, like a star or something, then it's going to just keep moving away and not feel the force being given to it by the parent star. I'm using astronomy analogies because those are rather classical, and in general, classical physics is very much easier to intuit than the stuff which you're going to really dive into when it comes to like the more microscopic scale. But back to the microscopic scale. So this is a problem, is what I'm saying, if it blows up to infinity like this. So this problem was resolved by Max Planck in the early 1900s, I think, yeah, literally the early 1900s, by his notion of the Planck energy. And that is basically, instead of this energy which would cause this basically radiation of light, so basically there is a relationship between energy and the frequency of light being emitted, since we're going by the case that light is being emitted as waves. The relationship between these two is not just a continuous distribution, but it's something that is quantized. The energy is emitted in packets, you could say. And these packets, the equivalence relationship between these were described by a constant, which is known today as Planck's constant. When heat is being radiated from some source, which is becoming hotter and hotter, it is done so in like integer multiples. So in very, you could say, discrete amounts, where this n stands for an integer. So this is interesting, and it is what eventually made this problem of the thing blowing to infinity go away, because instead of that, what you'd have now is a curve that looks something like this, which you still have your finite temperature, and it actually pretty much aligned with experimental observation of what certain materials would give in terms of the temperature when being heated and emitting light up to the ultraviolet range. So that solved that problem, but it introduced something new, and this something new wasn't based on anything classical. It was just Planck using the data which he will gather from experiment and making something up that works with the data. So this still needed to be explained physically as to what it actually entailed. But remember this, keep this in mind basically, that the ultraviolet catastrophe, as it was called, was solved by the Planck distribution. Building up to this was another problem, and that is the problem of if you have a material, let's say a particular metal or something, if you have a metal especially, that means that you have the nuclei of your metal here, and because they're metals, because you have free electrons in their conduction bands, you have free electrons floating about. I'm just going to draw a tree that can move about in the lattice structure of that metal. One thing which was observed, especially by the physicist Hertz in 1880 something, I think 1887 or something along those lines, was that if you shoot a light at such a lattice, such a metal lattice, then this light kind of is able to knock out one of these free electrons and basically give it a little bit of a momentum, give it a little bit of a push such that it can kind of scatter off of that metal lattice. This is interesting because up till that point, most people went with the notion that light itself mainly has wave properties. This was especially apparent after James Clerk Maxwell came up with his theory for electrodynamics with the Maxwell equations and saw the relationship between that and light. So from the Maxwell relations, it was realized that, well, oh yeah, light behaves like an electromagnetic wave with the propagating velocity, which is also very important. But the wave behavior of light kind of made people ignore the particle aspects of light, which was actually proposed back then, even in the times of Newton. So even in the 18th century, so in the 1700s, Newton came up with a theory of corpuscles, these particle quantities of light, which would have explained certain aspects of light in this case. But the wave nature of light paradigm kind of dominated for a long time, but it came into picture again when this problem presented itself by the experimental discovery of Hertz, the same Hertz which, if you took some introductory physics courses in high school or something, you might have heard of, since a unit of a frequency is a Hertz. But anyways, this problem was resolved by Albert Einstein in, if I'm not mistaken, in 1905, because that was supposedly the year people typically call the Annus Mirabilis. My Latin is bad, if not non-existent, but put the name of the thing here, and that is basically the year at which Einstein produced three very important papers which kind of revolutionized physics in a lot of sense. He produced his paper on special relativity, which some people suspect that his wife at that time really helped him with. Very interesting lady as well. He also produced this paper on Brownian motion, which explained how if you have pollen, I think, or something like that in water, why it has this random jiggling motion. And that was basically explained by actually tiny particles which you can't see, molecules basically of water, randomly bumping into that pollen and causing it to have that motion. And also he produces paper, very importantly, on the photoelectric effect. And this is what actually won Einstein the Nobel Prize, and nothing on relativity. So the way this was explained by Einstein is he took the idea of Planck, of Max Planck, with the Planck energy and the Planck distribution, and applied it actually to light. And basically that says that light can be explained as packets of energy that are basically, well, one, discrete packets, and two, that energy is what causes this electron to be kind of kicked off. And why that is important is because the main thing which Hertz noticed, and also people that further did the experiments, even Einstein noticed, is that the intensity of the light didn't matter, which is important. That means that it doesn't matter if you shoot it with one ray of light, two rays of light, three rays of light, or even like a million rays of light. If it is not of the right frequency, aka if it's not of the right energy, depending on the material, we're talking about, well, the material really matters in this case. But if it's not of the right energy, which kind of breaks that, you could say, that barrier of getting to the ionization energy needed, then this electron just wouldn't fly off. So even if it's a billion rays of light, if it's not of the right energy, then nothing would happen here. So the type of energy, aka the frequency of the light, really mattered. And in that particular case, Einstein could notice that, well, we can use that. You can use that Planck energy on light as well. And these discrete packets of light became what are known as photons, which is the particle, you could say, interpretation of light, which is very interesting. So after Einstein discovered the photoelectric effect, which has implication not only on later discoveries in physics, but also has application in a lot of sense, with, for example, the most popular one, I think, being solar panels, literally is an application of the photoelectric effect. You get the light ray from the sun bumping into some semiconductor, and that semiconductor basically allows electricity to flow. So due to the excitation of electrons, which kind of are emitted in some sort of capacitor type of setup, and creates this closed current, and that allows you to have electricity from the sun, basically from sunlight, which is really cool. The main direct application in our narrative right now is that of Niels Bohr. And Niels Bohr set out to tackle a very fundamental problem, and that was the problem of the atom. Back in the late 19th century and early 20th century, physicists were starting to just get a little bit of a glimpse as to what the atom actually was. Before that, people didn't have any idea as to how to go about things. As a matter of fact, chemistry, which is more closely associated with things like atoms and molecules, was primarily derived from alchemy, which was very well known back then to be like this gate-kept type of, not even science, but now we consider it to be a pseudoscience, of practitioners who were interested in probing the properties of, well, substances, basically, by doing experiments which were relevant for chemistry, like distillation, titration, and a lot of those things, but they didn't know exactly what was happening on the microscopic scale. The first glimpse of that came with people like Volta and especially Faraday, with things like the galvanic cell and some other interesting things regarding battery discoveries. But eventually, what really kicked things off was J.J. Thomson's discovery of the electron through things like the charge to mass ratio, which I've actually made a video about that you can check if you're curious. The charge to mass ratio kind of gave a glimpse of electrons being a thing, and even led J.G. Thomson to his plum pudding model, which was basically that everything is made out of these small, you could say, bodies, corpuscles again, which has negatively charged electrons in them, but it's surrounded overall by a positively charged like influence, like this whole ball basically, or this whole smear of influence was a positively charged thing, and it's called the plum pudding model because British delicatessen, being the plum pudding, looks like this, you could say, clumpy thing which has raisins in it, and the raisins would be the electrons. But after some time, and especially in the early 20th century, Rutherford came in with his discovery with using the gold foil experiment, in which he basically had a gold foil placed. My drawing won't be so good, by the way, around this spherical, or just not spherical, but this round disc-like detector, and from some sort of source which shoots out alpha particles, he looked at basically the tracks being produced by the alpha particles as they were detected in this disc-like thing. So basically, when shooting the alpha particles, which are charged particles, at the golden foil, they scatter off in different directions. And alpha particles are positively charged helium atoms, or helium-4 atoms to be more specific. So they're positively charged things that you're shooting at the gold foil, and if atoms in general were to be neutral, like you would kind of maybe assume with the plum pudding model, because of the negative charges balancing out the positive charges in that sphere, then these things would just shoot through, and you just detect maybe one intense, like you could say, focus of data points, because all of the alpha particles are just shooting out there. If they're deflected, it means they're kind of repelled or attracted maybe by some electric charge, or more importantly, they're deflected by some positive charge. And a positive charge basically gave Rutherford the insight that maybe instead of having that sphere of influence, you have the electrons basically orbiting some positively charged thing, which would be the nucleus of the atom, or rather what we know today as the proton. Rutherford didn't know about the neutron, and as a matter of fact, the neutron was discovered much, much later than what you would imagine it to be the case. But the picture still stands, basically, that if you have something positively charged, comes close to the nucleus of this, it kind of deflects because they're two positively charged things, and it kind of scatters off in different directions, which was what Rutherford found out. Now, this was interesting, but the main problem with this was classical electrodynamics. So, whereas the ultraviolet catastrophe or the black body problem was a problem of thermodynamics, this one became a problem of electrodynamics. And that is that if you have a positively charged thing with the electron kind of orbiting in this sense, then at some point, if something is orbiting the body, if it's in a perfectly stable orbit, then it might remain in that perfectly stable orbit indefinitely. But in this case, the electron is attracted by the proton ever so slightly. And even in the case of the solar system, if you're picturing something like astronomy, the planets aren't in perfect stable orbits. And after a long period of time, they actually will kind of spiral out of their perfect stable orbit and become something more chaotic. And in this sense, because of electrodynamics, if you have a moving charge, that moving charge will emit basically electromagnetic radiation. It will emit light. So what should happen here is that this electron, as it moves, continues to emit light, and that emission of light makes the electron lose energy. So it actually gets closer to the nucleus, and this continues to happen up to the point at which the electron should eventually spiral into the nucleus, and the thing should annihilate, and basically you wouldn't have an atom. So according to classical electrodynamics, electrons should spiral into the nucleus, and all building blocks of matter, which we know are made out of atom, would cease to exist. So there's also a problem And Niels Bohr solved this by grabbing the insights of both Einstein with the photoelectric effect and that of Max Planck in order to make his model of the atom, which if you've done any introductory chemistry course to your high school, again, this might be stuff, I'm repeating stuff that you've already heard very likely. But it's still nice to go through it because it all comes together at some point. With Bohr's model of the atom, if you have your nucleus, then you can have your electron orbiting the nucleus. It's a more complicated picture than that, but you can have your electron orbiting the nucleus. But however, because it can only have these finite energies, you could say, because of that discreteness which was introduced by Max Planck, then you'd have that the electron can be only in certain finite stable states, and it cannot occupy just any arbitrary state. So what I want to say with that is that the electron right here can only occupy certain finite energies because of Planck's, because of the Planck distribution, because of Planck's theory. So you can have n equals 1, n equals 2, n equals 3, sorry, this should be 3, etc., etc. And this is pretty nice. This would be what people call the ground state of the electron, and that is basically the lowest energy which the electron can have in this system. And if n goes up to infinity, which would be this, what this means is basically that the electron is no longer bound to the atom. This basically is just ionization. The electron is flying out if n goes to infinity. So this model gave this discrete picture of the energies which you can have for basically the electron. And how it tied the idea of Einstein into place is that if an electron wants to kind of promote itself from a lower energy level to a higher one, then it would need some sort of energy. And that energy would come in the form of light. If one shoots a light at the electron, we know from the photoelectric effect that that light can transfer some momentum to the electron. So if the light comes in some, you could say, energy package with the right frequency, of course, described by some h nu, then basically it can make the electron jump basically to a higher energy level. And this is coined as quantum jumping in sometimes. But quantum jump basically makes the electron go from one energy level to a higher one. It excites the electron. And if an electron is already in a higher energy level, let's say E2, and it loses energy, if it loses energy and drops to E1 back, then it emits a light with the same corresponding wavelength of the one which would otherwise excite one particle in the ground state to a higher orbital. So if this is a red, you could say, wavelength of light, so if this is red light coming in, giving this some energy and promoting it to E2, then if an electron drops from the energy level E2 to E1, then it emits a red light. So this is absorption and this is emission, which nicely ties into one thing which also was an experimental gap in physics, which was explained later with quantum mechanics, and that is atomic spectroscopy. People noticed for a while back that if you observe certain spectra of light coming from certain materials, so if you had a glowing tube of, you could say, especially back in the days, it would be something like some noble gases, or especially even hydrogen, though hydrogen was very rare to find. Instead of noticing a continuous spectrum, as you would notice, as was noticed, for example, with Newton, with his diffraction experiment, if you have the light ray of the sun coming in into a prism or something, it should break off into all of the colors of the rainbow. This was the thing which Newton observed classically when doing some optics experiment. You have a white ray of light, and that, as it diffracts through a prism, would kind of disperse into all of the visible colors of the electromagnetic spectrum. It was observed that with certain substances, pure elements, that this wasn't the case, and you would have this continuous distribution of light, so all of the colors of the rainbow, red, green, blue, whatever, whatever. But instead of having just those continuous distribution, you'd have these small black gaps, basically, which are very, very specific for each substance or each element, which was a bit of a mystery. So what the heck was going on there? And to explain that, you needed to have Bohr's model of the atom, because that explained that at certain energies, if you bombard a substance, say I have a gas cloud of whatever element you're interested in, I don't know, helium. If I shoot light through it, white light, so light with all of the colors of the rainbow, the whole spectrum, then some of it comes through, and that bit of it which comes through would be these bits which are filled with colors, but some of them are taken by the atoms in this cloud of gas, in this helium cloud of gas, because of this quantum jumping process, because some of the light is right at that right energy such that it promotes the electrons in a helium atom in this case. So that was a nice way at which Bohr's model explained some things which were later very important, especially for chemists, atomic spectroscopy. And the same thing was the case for emission, that if basically you have just a random cloud of helium, but that it is very high in energy, this is especially something which presents itself for astronomers, where you have basically that stars are basically these big, hot, glowing balls of gas basically in space. You have things that are very energetic and they emit light, especially as they're forming. So you have light being emitted from them. And the light being emitted from them, especially at the start or for particular processes, is not the continuous spectrum which you have with white light from the sun, for example, but it is some very specific, you could say, wavelengths of light which you see, and everything else is, well, dark, because it is not this nice white light, but it is a very specific color, like maybe some red, a little bit of yellow, or something else. So emission and absorption were both explained by Bohr's model. But the problem with Bohr's model is that Bohr, in essence, used his model to explain these different energy states in an atom, to explain things like atomic spectroscopy, but it wasn't especially very theoretically motivated, in the sense of it wasn't looking for any consistency with the theories that were being established. Max Planck theory, although he didn't have an interpretation yet for that, for his discreteness of energy, that came with Einstein, for example, when he used max energy distribution for things like the photoelectric effect. In a very similar spirit, Bohr was simply trying to see how these previously established models help with him kind of explaining the experimental results, which in this case was spectroscopy, with this new model. But how it exactly made everything that was previously established consistent, and what it physically meant, only came in with when the following two physicists became really interested in that problem, and that is Heisenberg, Werner Heisenberg, and Erwin Schrödinger. But before that, another thing which was crucial, experimentally at least, or two things which were crucial experimentally, was that another thing which alluded to the nature of light behaving like a particle. It's not simply the photoelectric effect, because that showed indeed the discreteness of light and showed that you can apply Planck's theory to explain that discrete package of energy as a photon. But the main thing which kind of gave hints to the particle behavior of light was something called Compton scattering, at which if you have some particle, whatever it is, being shot at with rays of light, so whatever that wavelength of light is, then it kind of transfer again momentum to that charged particle, so make that particle get a little bit of a push, like you would have in a classical case where you have a ball and you have another ball. So let's say these are two billiard balls and this one's standing still. You shoot that billiard ball back at the other one, It scatters off, makes this ball, let's call this one ball 2 and ball 1, makes ball 2 kind of go a little bit in this direction, and makes ball 1 go maybe a little bit slower in this direction as it transfers some of its momentum to the second ball. The same thing happens with light. As light interacts with a particle, some of its momentum is actually transferred to that particle, and some of its momentum of the wavelength scattering off of it is actually lost. So if you shoot it with, for example, an X-ray, then the outcoming ray of light, which you would detect with your sensor, would be something of lower energy. It might be something perhaps ultraviolet, or it might be something that is of a visible range of spectrum, so lower energy. And that is interesting because that also alludes to the fact that, well, light literally behaves like a billiard ball hitting a charged particle. So it transfers momentum like a particle would transfer momentum to another particle. So that further alluded to the particle behavior of light. And lastly, also another insight was brought by this student who was finishing his PhD, back then at least, and that it was Louis de Broglie, a French physicist. And for his PhD dissertation, he proposed something which at least his supervisor thought was rather radical, but now we take it at face value, and that is, instead of just light having this wave-particle duality, so instead of light acting as a wave and a particle, perhaps all matter behaves like waves and particles. So all matter which we know of can be described not just as particles, since we typically think of matter like solid matter around you as having like just being particle-like. He proposed this idea that even particles could have or will have wave-like properties, with wavelength which equals h, so Max Planck's constant, over the momentum of whatever actual particle you're describing, or whatever thing with mass you're describing. So this is, well, a rather insane thing to kind of wrap your hands around. It means basically that matter, physical matter like me and you, and the laptop you're watching this on, or the phone you're watching this on, this pen, all of them have some sort of wavelength right now. But the reason you don't notice this wave-like property of this pen, me, you, the device you're watching this on, is because you have some number which is ridiculously large, at least in comparison to the numerator, and that basically says that this is much bigger than this. Which is Planck's constant, which is a very, very small number. So if you have something very, very small divided by a very, very large number, well, the thing which that fraction gives you is something that is very close to zero, like 0.00000 something. And if you do the calculation, I remember reading that like a person has like a wavelength or a matter wave basically, which is like, I think some order of magnitude really ridiculous, smaller than even the nucleus of a hydrogen atom, so even smaller than a proton. So you could imagine that the wavelength which you would get from this for a person, for example, is super, super small. But this equation does become relevant, especially if you're looking at microscopic scales, where the mass of something like an electron and, well, the velocity could play a role as well, but there are nuances there. But where basically this fraction is not so close to zero anymore, where this fraction becomes something which you can notice becoming relevant, especially if you're working with experiments. And the de Broglie wavelength was actually discovered just a couple of years afterwards. So de Broglie proposed this, I think, in I forgot exactly, maybe 1927. Do I not? No, must be before 1927, sorry. Some time which I will put here. And a couple of years afterwards, two experimental physicists discovered the wave properties of an electron. So they discovered the diffraction pattern basically being produced by beams of electrons, the same way you'd get them with beams of light. So you'd have this glass tube setting, and with beams of light, if you shoot them, you'd get this diffraction pattern in which you have like these different rings basically of intensity showing up. And they notice the same thing when you shoot basically electrons, which is something that only happens when things behave as waves, because these dark circles are places where waves would constructively interfere, where you'd have peaks basically, and the places where there is nothing are places where the waves would destructively interfere. So when two waves basically kind of neatly cancel each other out and you get nothing. So it's very interesting that that particular thing showed up, and all of the problems basically stated were things which finally motivated the two people which, at the end of the day, individually discovered quantum mechanics. Werner Heisenberg, a bit earlier than Schrödinger, in 1925, he discovered quantum mechanics. And Schrödinger himself, which a lot of people know from the classic Schrödinger's cat analogy, also discovered quantum mechanics by basically himself. They both discovered something which would later be proven to be an equivalent thing and will be known as quantum mechanics. But basically the way they discovered it were through different formalism. Heisenberg's formalism is a little bit more abstract, though the more you work with some things with physics, especially even with QFT, we're going to notice that we're going to use Heisenberg's approach a little bit more often. And that is basically, he discovered it through something called matrix mechanics. And matrix mechanics uses, well, linear algebra, which was just back then recently being discovered itself by mathematicians. And he noticed that if you treat basically the states at which your quantum system could be in, such as, for example, in the case of Bohr's model of the atom with spectroscopy, if you treat the different states like N1, N2, and N3 as a matrix, which kind of tells you everything about the energy at which the thing could be in, E1, E2, E3, etc., etc., or basically, actually, besides calling it E1, E2, E3, let's just say they are actual states. So let's use the word states. So state. If you have your information for your quantum system described in terms of a vector, and vector in this case not being the same thing as vectors which you might be used to, like some vector which is described by x hat plus y hat plus z hat. So some vector in 3D space which would be described by an arrow. Instead of this picture, it is something a little bit more abstract and more along the lines of the way in which computer scientists or programmers would think about vectors, which is basically just a list of information. If you have this list of information, then you can have things, basically in this case, linear algebra comes a little bit in. You'd have something called a matrix, which can tell these different states how they should kind of behave if something is done to them. And Heisenberg's picture was that this matrix, or what you would call in quantum mechanics an operator, can tell the state how to transform from what it had before to what it has afterwards. And what it means basically is that if I have, for example, in the case again of the hydrogen atom, if I have my electron being at state 1, basically after you observe it, then that means that basically all of the information of the possible states which that electron can be in that hydrogen atom is still described by this vector. But if you observe it and you just have that one of them is predominantly like showing up, then most of these other ones perhaps might have a lower chance of being there. So that matrix makes sure that all of the information kind of collapses into just state 1 being very prominent and the other ones kind of dying out. So it adjusts the vector into the thing which you're looking for. And these operators turns out to be the things which you look at classically. For example, they could describe the position of whatever the particle you have is. So if you're not interested in the position of the thing, then you kind of have a matrix which have all of the information that you can possibly have about the, for example, X position of the states. It acts on the information about the quantum system itself and tells you what happens if you act on it. And operators are typically given with a hat, basically, in quantum mechanics. Perhaps I should remove this because this notation might confuse you. But yes, you have an operator which can tell you something about the position of the quantum system. You also have one which can tell you something about the momentum of the quantum system. And Heisenberg kind of worked with this matrix formalism, this linear algebra formalism of the theory which was building up. And eventually he found something called the commutation relationship between different operators. So what that means is basically he found the thing which tells you that if you act, for example, with the X the matrix first on the state. So if you look at the position first of your quantum system and then look at the momentum of that quantum system, so we have X acting on this and then have P acting on this, it is not the same thing as if you have basically P first, so momentum basically acting on this. So you measure the momentum at which your particle is moving first, and then the position. So the order at which you do this measurement really matters in quantum mechanics. And that eventually leads to something called the commutation relationship of the basically of the operators, which you don't have to exactly know what it is, but just in general that this in quantum mechanics does not equal zero. That kind of tells you that the order in which you look at things matter, and also leads very nicely into one thing which Heisenberg is famous for, and that is his uncertainty principle, which kind of tells you that there is this inherent uncertainty in basically measurements of different variables or different you could say physical properties of a system in quantum mechanics. And it's not due to experimental limitations, but it is an inherently built-in thing in nature, which is very fascinating, but we will definitely look at in a future video for our road to quantum field theory. So basically this allowed, at the end of the day, Heisenberg, when there's even a whole story with it, I think, that Heisenberg went to Denmark, I think, in the small peninsula, I think Helgoland, and he was going on a walk in the morning and he kind of had this idea. There's always a eureka story with these sort of things, but the story goes, if you're curious, that he went to Denmark, went to Helgoland, which is kind of like this fisherman's small peninsula, had this idea, then wrote up his paper on basically matrix formalism for quantum mechanics, and then basically tied in and finally gave an explanation for quantum jumps in the picture of Bohr's model of the atom, and also tied it all in with previously established things such as the Max Planck energy distribution and also some other noticeable things from quantum theory back then. That finally led to quantum mechanics. Erwin Schrödinger's picture is slightly different and uses more or less calculus instead of linear algebra, and we'll look at that now. Now, Schrödinger's picture was more so that, well, one, he was conceptually, you could say, inspired by some work in optics like Huygens, and how basically Huygens viewed that if you have basically wavelengths of light, basically, if you're describing, for example, things in geometric optics, like light, and like let's say this is the air, so let's say this is the air and this is the water, so a different material. If a light ray comes towards the water, you know that some of it might reflect, again, due to optics, and some of it might refract. So you kind of have this kind of angular bend, basically. This is purely due to optics, but after the wave implication of light was fully established, then there came into question why geometric optics would still kind of make sense. If you're talking about rays of light, which more or less would kind of describe a particle behavior, since it's like a straight line, basically, like a particle being shot at, that would have a straight trajectory. Waves oscillate. So how would you describe this? And the way in which Huygens kind of conceptually thought of this was that if you kind of look further and further away, then it would seem like, especially if the oscillation is really small, it would seem like you'd still look at the straight line. Like if the oscillation, instead of being so prominent, is teensy tiny small, then conceptually you can think of it as being just a straight line. Schrödinger was inspired by this because, of course, back then he already heard of de Broglie's postulate of matter waves. So matter waves being basically that wave property, but for example, for electrons and other small particles and just things in general. This kind of piqued his curiosity to look for a wave equation, just a general wave equation, which describes this matter wave. And basically that came into play, especially when he looked at something called the Hamilton-Jacobi equation, which is a very more particular niche thing, which I won't talk about, but let's stick with the analogy of Huygens and basically From that, Schrödinger's approach was, well, let's find the wave equation, which describes the matter wave. The quirky story with Schrödinger, by the way, if you're curious for general curiosity's sake, is that he went on this skiing place. I forgot the name of it exactly, but he went on this skiing place, might have been in Switzerland, with his mistress. So take from that what you will. And after a very long and exciting weekend, to say the least, he finally got inspiration to write his 4 papers, I think, on the Schrödinger equation and that's formalism basically and implications for the quantum theory, which was being developed. So quantum mechanics again, but in the case of Schrödinger, from a wave mechanics point of view. So Schrödinger, with his wave equation, basically looked for a differential equation, which was described by, now we use typically the Greek letter psi. And this Greek letter psi is a wave equation which is described by some amplitude most of the times with some exponential, which would be e to the ix. X can be whatever ambiguity of thing you're interested in for your particular solution to the wave equation. Schrödinger's main interest was looking at that matter wave without the interpretation of it yet, but just looking at the way matter waves behave and how you can calculate stuff with it. While Heisenberg's approach was more interested in describing the states of the quantum states, like not thinking of anything in terms of orbitals and such, but just states and how those states evolved by, in this case, using like matrix mechanics. But with Schrödinger, this was interesting because finally, at some point, he found the famous Schrödinger equation, which looks more or less something along these lines. So he finally found basically what is known as the Schrödinger equation, if the thing in this case, actually I should. So he finally found what is known as the Schrödinger equation, which basically is like F equals ma, but for that wave function. So what I mean by that is that F equals ma kind of gives you the equation of motion for the way at which whatever it is you have in classical mechanics behaves. Like if you describe F equals ma, which looks more or less like this, or more specifically, if you take note that acceleration is the second time derivative of position, so acceleration is basically second time derivative of position, then you can solve this equation and find x as a function of time, which would look something like what you might have seen in like kinematics if you've done like some introductory physics course. So you have x as a position of time. And that tells you everything about what you're describing. Like if it's a soccer ball being kicked, it tells you where the position of that soccer ball is, at least in the x like direction, at like you could say 2 seconds, 3 seconds, 6 seconds, etc., etc. Solving the Schrödinger equation does the same thing. Solving the Schrödinger equation, like this is a very complicated, you could say partial differential equation, but if you solve it, which is an exercise in calculus, it gives you the Schrödinger wave equation, which tells you how matter waves kind of behave, basically. Like it tells you how they evolve through time and space. And you can have things like the Schrödinger equation being independent of time. So the Schrödinger equation describing one state of, like, you could say the electron, like n equals 1. The Schrödinger equation just describing n equals 2 state, n equals 3 states. These would be called stationary states. Again, we will look more formally at these in other parts of our road to quantum field theory. And you can also have time-dependent solutions to the Schrödinger equation. And that is basically wave functions which not only depend on space, but also time. So basically, if you have it at state 1, instead of having just a snapshot picture of the wave-like properties of the matter wave, that matter wave can actually change over time, even if it's at the same, like you could say, energy level. So very interesting stuff will come up with using wave mechanics in that sense. But finally, to tie a bow on all of these things, the two last things which I want to talk about very briefly is, well, the interpretation of psi, like what psi actually means, and how those two pictures of Schrödinger and Heisenberg actually connects together and makes up quantum mechanics as we know it to be today, like in courses and such at university. So the interpretation of psi is very interesting because the wave function itself is something that is very mysterious. Like it's not something physical, like the matter wave, at least after the Solvay conference, which was like this conference in Brussels in Belgium, at which all of the, or a lot of the famous physicists from back then, like if you look at the picture, you see Marie Curie, Einstein, Lorentz, a lot of names which you've probably heard of from your like high school textbooks or something. They were all there at one place and they were hashing out the details of quantum mechanics. At the end of the day, Max Born, a German physicist, came up with the interpretation that if you take the modulus squared of the wave function, then you get basically the probability of whatever quantum system you have, like an electron being bounded by a proton. You have the probability of observing it in whatever n state it is in. So if you take the modulus square of that, then you have what you like the probability of the thing at the particular state you're interested in. If you generalize this, and if you say that, for example, you're interested in the small patch of probability of this quantum system, so if I want to look at the small patch of the probability of this thing, and let's say that this wave function doesn't depend on time, so the small patch, you're mainly interested in the spatial description of this thing, then that's this right here tells you the small, you could say, patch of probability of finding your quantum system in a particular n state over all directions in space for that particular small interval. If you integrate this over all bounds, over all possibilities, then you should get a value that equals 1, as that tells you basically that if you look at all of the possible probabilities of finding your particle in just one state, well, it should be 100%, because if you go look over all of the states, then eventually you should find the particle. It should be there. So this became known, especially this squaring of the wave function and integrating it, became known as the Born rule, or the Born, basically, you could say the Born statistical interpretation of quantum mechanics. It is very important. It's the thing which most physicists still work with, and it's the interpretation which we still attach to having the modulus square of the wave function. But the reason why I say there's still a little bit of exciting like ambiguity to it is because the wave function, if you don't modulus square it, people still don't know what that means. People still don't know what a matter wave actually means, what it means to have a matter wave. In terms of the Schrödinger equation, some people think that, well, the matter wave might be, well, you can't say anything about it until you square it and have an observable out of it, because it's only when squaring it that you get something which you can actually observe in a lab. But some people take the wave function more seriously and have things like the many-world or Everett interpretation of quantum mechanics, which I have talked a little bit about in this video, but it basically states that, well, that state, actually, if you collapse the wave function, as you would say properly, like, or decohere the wave function, if there's decoherence, then though you observe one state, all of the other states still exist, but they branch out in their own universe, which again is very out there. But if you read into these things, you can actually find good arguments for many of the interpretations. So interpretation of quantum mechanics is in it of itself an interesting question, which is still not fully hashed out, and one that some physicists think should be looked at a little bit more closely, because it is relevant for working with quantum theory. But because the Born statistical interpretation works really well, it is the one which people ran away with. But definitely would recommend you read into this, especially with maybe books, I think, like Helgoland by Carlos Rovelli, I think, the Italian physicist, or one which I'm reading currently, which I really like, is Physics and Philosophy, written by Werner Heisenberg. So there's that, and the way in which matrix mechanics and the Schrödinger, you could say, wave mechanics kind of ties together was through basically people like Paul Dirac. Paul Dirac, very famous physicist, especially because he tried to unify quantum mechanics with special relativity and came up with the Dirac equation, which eventually described the behavior of quantum system at relativistic speed. So at speeds very close to the speed of light, very fast moving electrons, for example. And from that equation, you even get antiparticles being predicted if you worked it out. And that's actually very interestingly how antiparticles or antimatter was kind of the discovery of it kind of progressed. So Dirac had his Dirac equation, predicted the existence of antimatter, and experimentally it was confirmed a couple of years later. So that's very interesting, but Dirac basically formalized things and kind of introduced something known as bracket notation. So the states at which you saw with the Schrödinger picture of, the Heisenberg picture of, you could say, quantum mechanics, this was all encapsulated by this new object called a cat, which is a very abstract thing, but it works, which is kind of like a column vector, and a bra, which would be described with this being on the other end of things, which is a transpose of the of the column vector. So it would be a row vector. But that detail aside, basically this gave a nice way of describing this state picture of, you could say, quantum mechanics, as basically if you have a general wave function, it can be decomposed into many orthonormal bases, or orthogonal bases in general. So it can be decomposed into psi1. It can be composed into, so a general wave function can be constructed out of these bases, which are psi1, psi2, etc., etc. To tie that picture in with what you might know from math, a vector, a three-dimensional vector, as I showed before, can be described as a construction of something multiplied by the different bases which makes them up. So what I mean by that is that if I have a vector, again, in Cartesian coordinate system, x, y, and z, I have a vector being made like this. The basis vectors are these small unit vectors called x hat, y hat, and z hat. And scaling up these vectors by different proportions and adding them together could give you this vector v. And it could, in essence, give you any vector in this Cartesian coordinate. It can give you any vector in what you would call this vector space. So these small orthogonal bases, and in this case orthonormal as well, but again, details will be filled later, span, you could say, this whole vector space. And that is the case in quantum mechanics as well. Like whatever state you have, you can kind of decompose it because of things being described linearly and with linear algebra. You can decompose it into orthonormal bases. And these orthonormal bases can span basically this vector space, which in this case, well, it would correspond with a wave function, but more generally, it corresponds to something called the Hilbert space, which again, we will look at the Hilbert space very, very closely, like in future videos, because there are more things to it than that. But that in general ties into how Dirac kind of we can morph things together, because if instead of having these orthonormal bases be discrete, if you make it continuous, so if I just remove these things, so if I just remove the notation of the cats and say that this is a general function that is built out of the smaller wavelength functions, which should be orthogonal to each other, but still smaller functions, then it ties back into the picture of Schrödinger. It ties back into the picture you have of, well, you deal with wave functions and what they do, how they propagate and such. So that's how you can shift in between both pictures and kind of get the coherent thing we have known as quantum mechanics. And I find this to be a very fascinating story. It tells you a story of how you have, I think, both types of physicists, which seems to be very prominent, and that I mean in the sense of some physicists like to look at experiments, see what the problems are that people have there, and kind of then say, okay, there's a problem there, let's find a theory which fixes this problem and inconsistency, and then worry later as to what the gap is. While you have some physicists which are more interested in the mathematics and the internal, you can say, consistency and logic behind the math, and then later worry as to the observational implications of their math. So what physicists would typically call the phenomenology of the theory. So We worry first on the math and then later worry on phenomenology, like how the theory could be tested and things like that. So I find quantum mechanics and its history to be rich in having both types of physicists, and I think just the history in general is very fascinating. I hope this part of our road to quantum field theory was useful to you and tell you why we use quantum mechanics to begin with before we start doing all of the math with bracket notation, integrals, and all of those things. That's gonna come, but this video was more of a primer for anyone actually curious about quantum mechanics. You don't even need to be someone interested in watching all of the playlists to learn quantum field theory. This in and of itself, I hope, is a nice intro as to what quantum mechanics kind of is and how we're going to be using it. So hope you enjoyed that and hope to see you soon in future videos. Bye bye. Also, as a quick final note, since I like, such as my journey to relativity, to tell you guys what sources I'm using, since I'm a student, and if you want to check these things, I completely understand. You should check them for yourself. The source I'm using is the textbook Quantum Mechanics Concepts and Applications by Nuruddin Sateli. It's a great textbook. I'm loving it, especially for my second quantum mechanics course. And I mainly use chapter 1, which talks about the history and motivation behind needing quantum mechanics. The first paragraph kind of neatly summarizes the whole thing I talked about in this video, but if you're interested in any of the small details, like specifically what the Compton scattering calculations were, what the black body radiation calculations were, or the photoelectric effect, there are paragraphs in the first chapter tackling the calculations for exactly each of those things. So definitely would recommend you get maybe a PDF of the book or something. And if you really want to work through things, then use that. This book's really good. Highly recommended for quantum mechanics.